Hi guys, so let's review a little bit about what we talked about today in our forces unit. So we said that the units of force are in newtons, which is equivalent to kilogram meters per second squared. And here you see an example of how we identify the force. Type of force is weight, normal, or tension for now. And then we use this on-by notation, where the first subscript is the object on which force is exerted, and then the second subscript is the object that is exerting the force. So here we go with the answers to the homework. So we see the normal force on A by the table and the weight force on A by the earth. And then diagram 2, the normal force on the box by the floor and the weight force on the box by the earth, and the applied force on the box by the man. And notice how these forces have the purple tick marks to show that they are equivalent in magnitude. And on the last free body diagram, we have the normal force on the box by the floor, the weight force on the box by the earth, and these two are not equivalent because you see here the tension force on the box by the person also contributes a vertical component of force. So there's a normal force in the upward direction and part of the tension force in the upward direction. And those two added together are equivalent to the weight force. So here's what we did in class. So we said, let's draw the free body diagrams when we add more than one book. Okay, so here's the free body diagram for A and B. And a little trick is, if you're not sure how to draw the free body diagram for A, you can always start with B, since B is the top piece on the table. Since B is on top, it's a little easier to start drawing that free body diagram than something that's sandwiched in between two other objects. So on B, we have the normal force on B by A and the weight force on B by the earth, and these are equivalent to each other. Now, if we have the normal force on B by A, in the opposite direction, there must also be the normal force on A by B. And then on A, we also have the weight force on A by the earth and the normal force on A by the table. And we said that since NAB and NBA are third law pairs, these three are equal. Okay, so these are third law pairs. Then we move down here to part F, and we said, well, these are the things we know from Newton's second and third laws. And so when it asks us to rank the magnitudes of the forces, we know that NAT was the largest, NAB was equal to NBA, was equal to WBE, and all of that is larger than the weight force on A by the earth because the book B had more mass. Okay, so now going back to the box on the ramp, we want to draw our box in the same orientation as the picture. So then we have the tension force on the box by the string, the normal force on the box by the ramp, and then pointing straight down to the center of the earth, the weight force on the box by earth. Okay, for the box on the ramp, what is the vector sum of all the forces in the free body diagram? Well, the net force in any direction was 0 because the system is in equilibrium, meaning it has an acceleration of 0. Okay, question F said, is the magnitude of the normal force of the ramp on the box greater than, less than, or equal to the weight of the box? Explain. And we said, well, we have to draw the coordinate system such that one of the axes, negative x for us, points the direction that the object would go, which means that we need to resolve the weight force into its components. So once we resolve it here, we get W cosine theta and W sine theta, and that's because of the ramp right here. Okay, so this angle is this angle, and so we are resolving weight onto the x and y axis. And then we said magnitude of the normal force was less than the magnitude of the weight force because the normal force on the box by the ramp was equal to W cosine theta, where W cosine theta is smaller than just W. Okay, so hope that helps. If you missed anything today, hopefully you got it out of the video, and I will check your homework next time I see you. Have a good night.